There's something off about 3I/Atlas. During late July, premier observatories such as Hubble and JWST gathered remarkable observations of this uncommon interstellar comet. Right when its coma expanded beyond 300,000 kilometers and accounts surfaced of a greenish hue plus unusual intensification, the formal announcements suddenly ceased. NASA pointed to solar positioning and precautionary protocols. Yet this sudden quiet feels conspicuous, especially compared to the quick succession of disclosures from Oumuamua and Borisov that stirred up so much excitement. Such a lack of details isn't merely sparking outlandish speculations. Failing to deliver prompt explanations risks eroding confidence in the process of sharing astronomical breakthroughs. So, what's behind this information blackout? And what details are being withheld regarding 3I/Atlas? On July 21, 2025, the Hubble Space Telescope zeroed in on 3I/Atlas, snapping the clearest photos to date of this cosmic wanderer. 2.5 weeks afterward, on August 7th, those shots were released to the world, depicting a core measuring no more than 5.6 kilometers wide and an extensive dust stream extending toward the Sun. By August 6th, the James Webb Space Telescope stepped up, employing the NIRSpec tool to collect spectral readings. However, for JWST, just basic summaries and initial remarks made it out publicly. No standout visuals, only suggestions that evaluations were in progress. Gemini South got involved on August 27th, obtaining photos that verified the comet's vigor and tail development. That material hit the Open Database on September 4th and 5th, offering scientists and hobbyist stargazers fresh views of the expanding coma and evolving dust patterns. Every drop sparked lively web conversations, though the gaps between updates began to stretch out. Following September 22nd, things shifted. No additional top-tier photos, no updated datasets from Hubble, JWST, or Gemini. The stream of authoritative reports dwindled to a trickle. For those following the comet's journey, the void was glaringly obvious. What was once a rhythm of consistent unveilings now revealed an expanding silence. The puzzle extended beyond what had been spotted to why further insights weren't forthcoming. Viewing 3I/Atlas through Hubble or JWST goes far beyond aiming and capturing. Each scope operates under rigid solar exclusion guidelines, operational constraints designed to shield their fragile lenses and sensors from unwanted solar glare. Hubble's policy is straightforward: nothing within 50 degrees of the Sun. JWST, equipped with its enormous sun shield and finicky infrared detectors, imposes an even tougher 85 degrees buffer. These thresholds are non-negotiable, embedded deep in the framework. Should an object edge too near the Sun's sky location, the programming blocks any scheduling or execution efforts. The dangers are far from hypothetical. Unfiltered sunlight might scorch the gear, irreparably harm sensors, or jeopardize the whole endeavor. As 3I/Atlas traced its route, the solar elongation, the separation among the comet, our planet, and the Sun, narrowed steadily. Late August saw it breach Hubble's 50 degrees boundary. Shortly after JWST's August 6th NIRSpec session, it surpassed JWST's 85 degrees line. From there, both facilities imposed a mandatory pause. The experts at the Space Telescope Science Institute, responsible for timetables and functions, simply couldn't proceed. The restricted areas are programmed into the planning software. Bypassing them would activate emergency shutdowns and might suspend all research until thorough checks. This stems not from red tape, but from unyielding physical realities. Even pressing target of opportunity, bids can't skirt these zones. The sole path forward is patience until the alignment shifts. For 3I/Atlas, that translates to no fresh premiere photos or readings until the elongation widens once more, something trajectory models forecast for early December. In the interim, the restriction persists, leaving the leading telescopes quiet, not from reluctance, but from necessity. Clues to 3I/Atlas's actual makeup started emerging as initial research outputs appeared. Hubble's July captures displayed not only a dust trail but a vast coma, a shell of vapor and particles spanning almost 348,000 kilometers. That's over a quarter the width of the Sun and vastly outsized for comets this far out. The standout revelation arose from preliminary spectral insights. Experts began murmuring about an exceptionally robust carbon dioxide presence in the coma. To clarify, by late September, no formal, vetted quantitative analysis has verified carbon dioxide as predominant, yet the indications persist, and the research groups haven't refuted them. For an interstellar body venturing into the inner solar system on its inaugural pass, such a composition would offer a significant chemical revelation. Typical solar system comets lean heavily on water ice at this proximity. Meanwhile, alongside the sanctioned updates, backyard skywatchers matched the effort with their independent sightings. A number noted a clear verdant shade in the coma, probably due to dicarbon or psi anomalous features marked the classic cometary signatures in this object's chemistry, but with a notable difference. Certain watchers pointed out that the green hue appeared more vivid and enduring compared to standard comets. Lacking comprehensive spectral analysis, however, it's challenging to identify the exact reason. The sunward plume, initially imaged by Hubble and later by Gemini, also drew significant attention. Its form and intensity appeared to vary day by day, fueling discussions on whether outbursts from the surface or observational angles were responsible. Brightness measurements via photometry introduced further uncertainty. Data from both hobbyists and experts varied considerably, at times by over a full magnitude. While some discrepancies stem from tools and calibration differences, others might indicate genuine quick fluctuations in the coma or nucleus. As major observatories remained unavailable, these inconsistent ground-based observations served as the primary insight into 32/Atlas's behavior. Currently, the most reliable information suggests a comet featuring an unusually large coma, potentially rich in carbon dioxide, a sunward plume, and a coloration that defies easy categorization. Without fresh data from leading telescopes, each irregularity sparks conjecture and underscores our dependence on sporadic contributions from amateurs and terrestrial observers. By the end of September, the quiet surrounding 32/Atlas extended beyond mere technical issues. It began to feel deeply personal to those monitoring it from Earth. Online forums buzzed with irritation and theories. One hobbyist astronomer posted, "It's like pursuing a phantom. Night after night, we're left wondering what's truly unfolding up there." Another questioned, "Why aren't we getting the unprocessed data? What's the holdup?" In reality, the journey from telescope observations to public access is far from immediate. Data from Hubble or JWST enters a holding pattern upon receipt. After downlink, it undergoes calibration, cosmic ray removal, detector anomaly fixes, and background adjustments. For JWST, the procedure is particularly intricate. NIR-spec spectra go through several software pipelines, with specialists verifying for glitches or calibration flaws. A single oversight could lead to mistaking a false chemical signal for the real thing. On top of these challenges lie institutional guidelines. Hubble and JWST both enforce proprietary phases, typically 6 months for Hubble initiatives and up to a year for JWST ones. Lead researchers, or PIs, receive exclusive access first, a custom designed to honor those who crafted and secured the observation slots. Although some PIs opt for quicker sharing, others hold off until their groups have scrutinized and validated every detail. This is particularly the case for prominent subjects like 32/Atlas, where hasty announcements might stir up the research world and media alike. Organizational protocols pile on additional steps. Press statements or key visuals must navigate approvals from entities such as NASA, ESA, and occasionally CSA for JWST. Teams assess the content, scan for legal or agreement concerns, and align on release schedules. Even straightforward datasets can linger for weeks in this approval cycle, pending clearance from science leads and PR experts. For 32/Atlas, the timeline dragged on as groups evaluated the dangers of sharing partial or unclear findings. As a JWST team member observed, better to deliver accurate results eventually than erroneous ones in a rush. Interstellar objects offer no do-overs. Consequently, even as enthusiasts and volunteer scientists crave fresh info, the formal pathways proceed deliberately. The frustration of lingering with outdated visuals amid circulating whispers is inherent to the setup. To many in the field, this gap resembles a barrier. To planners and processors, it's a safeguard emphasizing prudence over concealment. Yet as the hush persists, it increasingly influences the discourse, transforming standard delays into sparks for guesswork and everyday vigilance into growing discomfort. Speculation about 32/Atlas proliferated right after the Premiere telescopes fell quiet. Some discussions attributed the information gap to secret detectors, implying that defense or spy satellites had captured shots forever hidden from view. Alternative views focused on averting alarm. The notion persisted that officials were curating the narrative, withholding details to prevent sensational reports on an extraterrestrial oddity. A faction even argued that the observations were simply too bizarre for swift disclosure, that experts were urgently trying to interpret phenomena outside conventional models. The news environment only intensifies this. Accounts of comets like Neowise or Borisov, striking, observable, and visually appealing, dominate social feeds and news rankings. Their accessibility turns them into digital magnets. Content about visible evening sky events drives engagement. Meanwhile, 32/Atlas, hampered by irregular reports and complexities, slips from the spotlight. In the void of novel visuals, conjecture rushes in to fill the space. After the Gemini South images released at the start of September triggered a massive surge in social media buzz around 2I/Borisov, reaching engagement levels tenfold above the norm for comets, before veering into conspiracy-laden tags amid the ongoing delay in further details. Yet the truth operating behind the curtain proves far less sensational and much more systematic. Observations from telescopes like Hubble or JWST undergo a rigorous, multi-step workflow before reaching anyone beyond the core instrument group. Initially, the unprocessed data get transmitted earthward and labeled with satellite status info. Next, standardization procedures activate. Interstellar radiation gets filtered out, sensor anomalies fixed, and ambient noise deducted. For JWST specifically, this involves navigating no fewer than 3 primary phases: device-specific fixes, tool-specific tuning, and sophisticated handling such as image merging and flaw elimination. Every phase gets scrutinized for glitches, marked for oddities, and occasionally reprocessed if irregularities appear. When the dataset achieves scientific usability, the lead researchers examine it, typically during a restricted access window, 6 months for Hubble, extending to a full year for JWST. Only once the PI and their collaborators feel assured of the findings does it advance to the subsequent checkpoint, oversight from the agencies. NASA, ESA, and occasionally CSA all provide input, scrutinizing legal, agreement-based, and research-related concerns. Release coordinators synchronize the rollout timing, occasionally holding off for days until full approval. Should the information be unclear or suggest unforeseen elements, the timeline drags even more. Hasty announcements, particularly for a spotlight-grabbing object like 2I/Borisov, could lead to embarrassing revisions or outright withdrawals. This stands in stark opposition to prior interstellar intruders. Oumuamua's 2017 detection saw information flooding out nearly live, draft papers, lively discussions, and outlandish theories all surfacing online in mere days. Borisov, arriving 2 years afterward, adhered to a predictable, by-the-book rhythm. Images and spectral analyses dropped right on cue, with minimal fuss for Borisov. The blend of engineering challenges, deliberate vetting, and cross-organization approvals has fostered a halting, irregular data stream. This setup brews an ideal environment for gossip and impatience. Still, underneath the chatter, the system chugs along methodically, phase by phase. Each element crafted to spot errors prior to public exposure. For those engineers and data experts immersed in it, the focus isn't on concealment or narrative management. It's ensuring the research holds up, regardless of the extended delays nobody prefers. The upcoming Mars encounter on October 3rd offers the prime chance for fresh insights on 2I/Borisov. At peak proximity, the comet will zip by merely 0.19 Australian dollars from Mars, roughly 28 million kilometers. That's relatively near on a universal scale, yet still too distant for any fine-tuned snapshots. The ExoMars Trace Gas Orbiter, or TGO, hosts the CASIS instrument, renowned for its crisp 5-meter per pixel views of Mars terrain. However, from that range, CASIS encounters strict optical constraints. Optimistically, every pixel would span over 300 kilometers. The core of 2I/Borisov, measuring between 320 meters and 5.6 kilometers wide, would register merely as an indistinct speck. Zero features, no outline, just a dim glow amid the stellar backdrop. HiRISE aboard the Mars Reconnaissance Orbiter, boasting a bigger lens, manages slightly finer resolution, around 34 kilometers per pixel, but that's woefully insufficient to discern the core or features in the surrounding dust cloud or trail. These instruments were engineered for detailed Martian charting from nearby orbits, not for pursuing swift celestial wanderers in the void. Following a comet at such orbital velocities doesn't fit their operational script. Shutter speeds must stay brief to prevent blurring, and the clarity-to-interference ratio plummets as the object dims farther out. Thus, what practical contributions can Mars satellites provide? Brightness profiling, gauging the comet's luminosity at a juncture when ground observatories and Premiere scopes are blinded by solar positioning. Spotting a pinpoint object from Martian orbit aids in monitoring the path and vigor, particularly amid any abrupt flares or luminosity shifts near the pass. The handling chain moves swiftly. TGO and Mars Express can relay and refine these captures in just 1 or 2 days, assuming no glitches. Yet for those hoping for stunning magnified shots, it's wise to temper hopes early. The Mars Pass emphasizes opportunistic timing over intricate visuals. Its true worth emerges in filling an observational void when all other vantage points must avert their gaze. Closest solar approach for 2I/Borisov hits on October 29th or 30, with the comet sweeping within roughly 1.36 Australian dollars of the Sun. At such a remove, it avoids being a typical solar skimmer, though the intense warming and brisk pace impose genuine strain on the nucleus. So, as the comet navigates its solar closest point and surfaces anew in December, what indicators merit attention? Start with the brightness pattern. Abrupt surges, notably brief and intense ones, might indicate crustal breakup or eruptions. Yet a gradual climb and decline aligning with projections, as it approaches and withdraws from the Sun, would align with standard behavior. The Sun's position suggests a consistent volatile emission instead of a complete split. Keep in mind, one sudden increase in brightness doesn't indicate breakup. It's essential to observe a trend, preferably validated by several independent viewers. Then, examine variations in the antitail, that spike directed toward the Sun visible in broad-field photos. With Earth's movement changing its angle to the comet's path around the Sun, the antitail might twist or weaken. For 3I/Atlas, the antitail's visibility ought to reach its height near perihelion, fading quickly as the alignment shifts through December. Monitoring how it aligns in various images serves as a key method to verify orbit specifics and dust patterns. Colors play a role as well. Should the green shade noted by hobbyists vanish or alter post-perihelion, it might signal the depletion of particular compounds as ices on the surface evaporate or new layers get uncovered. Yet, only spectroscopic analysis can verify the actual shifts. Photos by themselves can deceive. Come December, with the comet's angular distance from the Sun growing and Premiere observatories freeing up time, anticipate fresh rounds of detailed photos and spectral exams. Peering toward 2026, an advantageous setup involving Jupiter might provide yet another chance for observation if 3I/Atlas endures its close solar brush. At present, the sharpest approach is a discerning perspective. Contrast photos from different times, verify brightness measurements against each other, scrutinize bold claims, and recall that hues don't equate to composition absent spectral evidence. Astronomers worldwide, spanning experts to home-based watchers, are monitoring collectively. The narrative continues unfolding. It's merely flipping to the subsequent chapter. Regulatory reports highlight operational hurdles. Hubble's 50 degrees limit and JWST's 85 degrees sun avoidance zones, combined with extended data processing periods and rigid exclusive access rules. Even with such justifications, the lack of immediate insights into an interstellar visitor featuring a carbon dioxide-rich envelope, a sun-facing jet, and hints of verdant coloring has kept key research puzzles unresolved. No published, vetted spectral data detailing the envelope's makeup exists yet, and the scattered brightness variations' deeper meanings linger unexplored. As satellites circling Mars gear up for a near flyby at 0.19 astronomical units, forthcoming photos and spectra, delayed by 24 to 48 hours in transmission, might at last ease the data flow jam. For the moment, the 32/Atlas scenario illustrates how procedural restraint and equipment barriers influence the global view of these exceptional solar system guests, what gets revealed and what stays hidden.